In this video lecture, we will investigate how and where on planet Earth magma is actually generated. According to this pressure-temperature diagram, the rock beneath both continents and oceans is solid. For melting to occur, some environmental change must bring the pressures and temperatures of the rock to those of the solidus curve. As it turns out, there are three ways to do this. One would be to simply heat the rock. If we do this, we could eventually meet the conditions described by the solidus line and melting would occur. So, if we want to consider some chunk of rock here, and we want to melt it by adding heat, we're going to add the heat, which raises that rock's temperature. Okay, we're going to raise the temperature up until we cross that solidus, at which point the rock will begin to melt. Another option would be to decrease the pressure. If we start by considering that same sample of rock, and this time we let it rise up towards the surface, because remember, depth and pressure are synonymous in this instance. So if we let our sample of rock rise up through the earth towards the surface, then the pressure on that rock will decrease until it reaches conditions described by the solidus line and melting occurs. This is called decompression melting. Importantly, no change in temperature is required for decompression melting to occur. The third and final way to melt rock is a little weird. It turns out that if you add water to solid rock, you can actually move this solidus line, changing the pressure temperature conditions at which rock begins to melt. On the diagram, this is typically represented by drawing in a new solidus line to the left of the original. Now, sometimes it's okay to draw that in as a straight line or as a parallel line, like I've done. However, on the real planet, it actually looks more like this. Regardless, in the case of flux melting, the rock doesn't change position and it doesn't increase its temperature, but melting occurs anyway because somehow water has made its way into the rock, which changes the pressure temperature conditions of melting, making it such that that rock melts just at the exact same temperatures and pressures that it already was. The word that we have for this, the mechanism, is called flux melting. So the three possible ways to melt rock include adding heat, decreasing pressure, and adding water. This still begs the question though, where on planet Earth are each of these different mechanisms actually active? Can you take a guess? If you guessed plate boundaries, great job. We know that melting happens at plate boundaries because these are the locations where almost all of the volcanism on the planet is actually found. So next, we'll consider each of the melting mechanisms in turn, and we will relate those physical mechanisms to the actual types of plate boundaries where each physical mechanism operates. We will start with the addition of heat. Now, as it turns out, adding heat is actually not a very common way of melting rocks inside of planet Earth. Also, surprisingly, in most instances where the addition of heat is responsible for melting, it's not actually the only process involved. Because of these complications, we will cycle back to the addition of heat as a melting mechanism at the end of the presentation. Now, decompression melting, on the other hand, is quite common. In order for this mechanism to work, all you need to do is to decrease the pressure acting on a rock. This decompression occurs anytime a sample of rock that exists at some depth is forced, and is forced vertically upwards towards the surface. can you think of a plate boundary where this might be happening? If you thought of an oceanic divergent boundary, great job. So here's my two oceanic plates. They are diverging, and this is creating a mid-ocean ridge, which we all remember is an underwater volcanic mountain chain. And the reason melting happens is because this bit of mantle moves upward, which causes it to melt. At these boundaries, material rises up from the mantle and melts and continues to rise and then erupts at the mid-ocean ridge as lava, creating new oceanic crust. The decrease in pressure experienced by the rock as it rises eventually enables it to melt. So here we have melting happening right in there. This melt then continues to arise, eventually erupting at the mid-ocean ridge, right there. All of this is possible without any associated change in temperature. The rock is not heated up, it's simply decompressed. Next up is flux melting. Can you think of a type of plate boundary that might be capable of introducing water into some portion of rock? If you thought of a subduction zone, great job. They have volcanoes. There we go. So it turns out that oceanic plates actually have a lot of water inside of them. Seawater seeps in through cracks and fissures in the rock, and that water is then captured inside of the pore spaces and inside of certain minerals. When that oceanic lithosphere subducts, the pressures and the temperatures increase, and that forces the water to boil off. Here it is again. The water is being heated up here, and it's being driven out of that subducting slab, entering up into the mantle rock above, right? So here is our slab, and this is mantle rock above, which is all solid. But when this water enters, it causes melting here, and then that melt rises upwards. The addition of water changes the physical properties of the rock such that melting occurs. Note that the water does not change the temperature of the rock at all. It simply lowers the temperature at which melting can occur. It's important to recognize that the oceanic slab itself does not melt. What happens to the subducted slab, this part here, is actually being actively investigated by scientific researchers. Some researchers believe that we have evidence that indicates that the oceanic lithosphere breaks off and rises up to float beneath the continents. Let me just try to sketch that for you real quick. Continents. This is my volcano. Now maybe there's little slabs of oceanic lithosphere hanging out here underneath the continent. That's one possibility. Other data appears to show that there are slab graveyards down at the core mantle boundary. And you might have a bunch of oceanic slabs just sort of hanging out down there. We have evidence for both. This is, of course, not to scale. Well, the fate of these subducted subducted slabs is outside the scope of this class. But what you should remember is that they absolutely do not melt. Also, they don't magically pop out again at the mid-ocean ridge. It is not possible for already existing crust to appear at a mid-ocean ridge. Okay, this brings us back to the addition of heat as a mechanism for melting rock. As it turns out, little, if any, initial melt generation is due to the addition of heat. However, this can be an important secondary source of melting. Let's take a look. If we zoom in to a subduction zone or a hotspot volcano, hotspots we haven't really discussed in this class, but they are locations on the Earth where you have really, really deep magma coming up to the surface in very large volumes. In both of these cases, you have magma coming up from depth, and it has to traverse through the lithosphere, and as part of that, it goes through the part of the lithosphere that is mantle and up into the part of the lithosphere that is crust. So if we zoom in, we will find that magma generated in the lithosphere, in the case of a subduction zone, that magma is generated via flux melting in the lithosphere. And remembering that the lithosphere is indeed comprised of both crust and mantle, the initial melting we can see happening in the mantle, and that magma rising upwards through the mantle. It does that because it's less dense than the surrounding mantle material. So all of this out here is still mantle. However, once the melt reaches the continental crust, it's forced to stop. Continental crust is lower density than that melted mantle rock, and so the melt has to stall at this point. It stalls at the base of the crust. Of course, the melt itself is incredibly hot, and its presence here heats up the continental crust so much that the rocks of the continent begin to melt. Then one or both of these melts can continue upwards through the crust towards the volcanic arc, resulting in volcanism at the subduction zone, of course, on the overriding plate. In summary, decompression melting happens at the mid-ocean ridge where mantle material is forced upward, causing it to melt. Flux melting occurs at subduction zones, both oceanic-oceanic and oceanic-continental. It happens when water is boiled off of the subducting slab. This water then moves up into the mantle above, decreasing the temperatures at which that material melts and causing the material to melt in place, right here for example. And finally, melting due to heating, which is a secondary process wherein hot magma is forced to pool at the base of the crust due to density differences. The addition of heat to the base of the crust then causes crustal material, for example here, its temperature increase, its temperature increases, causing it to melt in place. While all three mechanisms do contribute to the melting of rocks on Earth, decompression and flux melting explain the initial generation of magma at both the mid-ocean ridge and subduction zones. Melting via temperature changes is not a dominant mechanism for planet Earth. This concludes the Mechanisms of Melting Rocks video lecture. See you next time.